In this video, we are going to recall the most important concepts about disk partitioning, volumes and file systems. Then we are going to introduce the Sleuth Kit and explain the functions of its various categories of tools. Finally, we are going to show their usage analyzing the NTFS file system of an acquired image. The first sector of a disk is the so-called master boot record that contains the bootstrap code and the partition table. The partition table contains the entries with information about each partition on the disk. A partition can be defined as a set of contiguous sectors of a disk formatted with the same file system. Older computers that relies on the master boot record can have a maximum of 4 primary partitions, though extended partitions can be created. Newer computers that have the unified extensible firmware interface uses the globally unique ID partition table that allows up to 128 primary partitions. The partition table itself is not usually of great interest to the forensic examiner, unless there are some partitions to be recovered due to the partition table corruption. A great tool to recover partitions is TestDisk, installed on Kali Linux that can also work on raw disk images. A volume is a logical set of data that can be formed by one or more partitions. A volume may even span across several physical disks, while a partition can only reside on a single disk. A volume, like a partition, can be associated with a single file system. A file system defines the storage, organization and management of data on a volume. Data is usually organized into files and directories. A file could be formed by one or several blocks or clusters, that are the smallest data units available. Generally, on modern file systems, blocks have a size of 4 kilobytes. The information associated with files or directories are organized into 3 layers on the file system: the file name, data and metadata. The file name stores the name of the file and the pointers to its metadata. The metadata contain all the other information about the file or directory, such as the owner, the timestamps, the permissions, and the pointers of the data blocks. The data blocks are where the actual contents of a file are stored. Having introduced the fundamental concepts about disk partitioning, volumes and file systems, it's now the time to show how to practically analyze a file system using the Sleuth Kit. The Sleuth Kit is a suite of file system forensic command line tools developed by Brian Carrier, one of the major experts of file system forensic analysis. It is based on part of the code of the Kernel's toolkit, created in the late 90s by Venema and Farmer. While the kernel toolkit can only run on and be used to analyze Unix-derived operating systems, the Sleuth Kit is multi-platform and supports many different file systems. Can also analyze different image formats like the RAW format, the EWF and the AFF.
The Sleuth Kit can be downloaded from its official website sleuthkit.org. While for the Windows platform you can directly download the binaries, on Linux and macOS you have to download and compile the source code.
The Sleuth Kit tools are divided into groups or categories depending on the layer on which they operate and the type of function they perform. The tool's naming convention follows a well-defined scheme. Indeed, the prefix of the name of the tool indicates the layer. For example, MM are for tools that operate at the volume layer, FS at the file system layer, BLK at the data unit or block layer, I at the metadata or inode layer, and F at the file name layer. Instead, the suffix of the name of the tool indicates the function, and take the name of the analog Unix command. For example, stat that displays general information about the queried item, ls that lists the contents of the layer, and cat that dumps the contents of the layer. There are also other tools of the Sleuth Kit that don't follow this naming convention. Very well, so we are ready to analyze a file system, and we are going to use as a practical example the image that we acquired in the video Drive Imaging with DC3DD in the previous section. Remember that the image we acquired was split into 13 files, so we could ask ourselves how to deal with this issue. Don't worry, as the Sleuth Kit tools can also work on split images. The highest layer is the volume layer, and the first tool we are going to introduce is MMLS, that displays the layout of the partitions in a volume. We move into the directory where we have saved the split images and list its contents. Then we execute MMLS, giving as input the name of the image file, followed by an asterisk to include all the image files. The output shows the partition table type, that is DOS, the sector size, that is 512 bytes, and the contents of the partition table. The output is very similar to that of the fdisk tool, with the difference that MMLS also shows the unallocated sectors of the disk and displays the partition offsets in number of sectors. In this case, there is only one partition formatted with the NTFS file system. We will cover the analysis of unallocated sectors in section 4, that is about file carving and data recovery. To have more information about the file system, a tool that begins with the prefix fs can help us, fsstat. From the output of MMLS, we see that the NTFS partition starts at sector 63. So we have to specify this offset with the fsstat command, with the O option. The output shows very detailed information about the file system, including its type, the volume serial number, the operating system version, and then in the second part, metadata information such as the location of the first cluster of the MFT, the master file table, the size of MFT entries, and the MFT entry associated with the root directory, that is number 5. Then it shows other information such as the sector and cluster size, and below the different file attributes. The master file table contains the file system metadata and the entries for each file and directory. The file system metadata is organized is stored in special files that begin with a $sign and that are saved in the root directory, but are not visible using Windows Explorer. To also display these files, we can use the FLS tool instead. By default, the output lists the contents of the root directory, showing one row for each file or directory. At the very left of the row there is the file type, where R stands for a regular file and D for a directory. Next we have the metadata address, where the first number of the left indicates the master file table entry, while the subsequent numbers the attribute type. For example, 128 indicates the data attribute. Next we have the file name. The first 16 entries of a master file table are reserved for the special files that begin with a $sign. For example, the master file table entry number 0 is associated with the special file that stores the metadata about the master file table itself. FLS can also display deleted entries only. For example, if we want to extract all the deleted files of the entire file system, we could execute the same previous command, adding the RDP options, where R stands for recurse into directories, D for showing deleted entries only, and P shows the full path of each entry. We can notice that deleted entries present an asterisk between the file type and the metadata address. FLS also has an option, that is option M, to create a body file for the generation of a timeline with the MakeTime tool. And in this command we have also to specify the body file. Another command that can also generate a body file for the generation of a timeline is ILS, that lists the master file table entries, that lists the structure of the master file table entries. And we can specify the same option M to generate, and the body file to generate the body file. To display the details about a single master file table entry, we could execute the istat tool. For example, we can see the details of the master file table entry 0 that is associated with the $MFT special file. The last number is the master file table entry. The istat output shows various information about the entry, such as the ownership, the security ID, the timestamps, the file attributes, and below all the data clusters. We could stream to the output the data of a single cluster with the blkcat tool, and then pipe the output to the XXD viewer to display its contents. We could display, for example, this data cluster. This is the offset in sectors of the data cluster. And then pipe the output to XXD. And so we can see its contents, the contents of this particular data cluster. Another useful tool of the block layer is blk-ls. By default, it copies the contents of all the unallocated blocks of the volume to the output. The output then could be redirected to a file and used as input for data carving tools to recover deleted files. Deleted files could also be recovered manually using the Sleuth Kit tools, as we will see in section 4. Then finally, just a few words about the MakeTime tools. MakeTime can be used to generate a timeline of a file system activity, taking as input the body file generated by the FLS or ILS tools. So if we would like to create a timeline from the previously generated body file, we would execute this command.